So now we find ourselves with a change in speed. We left off. When we left off, it's almost like this is a web series or something. When we left off, we were working with a graph that looked like this, where velocity was changing over a certain amount of time. Well, it turns out that we can call that something. We call that something acceleration. You've probably thought of acceleration as going faster, and that is true, certainly. But a more accurate description of acceleration is it's a change in velocity in a certain amount of time. Now, that equation, pretty simple, looks an awful lot like the previous ones, and that is A equals delta V, so change in velocity over time. I'm going to not write the delta T because I don't care to. Now, average acceleration is going to be how much the speed changes from beginning to end, right? Just like we did last time. I don't need to write out average here for now because we're going to end up using this here in a moment. Now, another way to write this is like this. I'll rewrite the whole dang thing. A equals VF minus V initial over time. Okay, so now that little O, that little zero, remember, means initial. Okay, that's what that little zero means. Now, we can rearrange this equation if we like, and we will here in a few moments once we get to the next section. Now, instantaneous acceleration, slope of a velocity time graph. So, like we were doing before with velocity and speed, now we can do the same thing with a velocity. Oh, sorry, not velocity. I know how to talk. Like we were doing before with a displacement and time graph, now we can do a velocity and time graph. So, let's say that we have a graph that looks like this, okay? We've got a velocity that is increasing over time. So we look at our little thing here, we put our ruler down, and we see that it is a positive slope. So that means that the speed or the velocity is increasing over time. So it started at 0 right there, and it goes up to some other velocity at the end. If we wanted to find the acceleration, we just plug in those various things. So why don't we just label this graph here? This top part, let's say this is 5 meters per second right there. This is 0 meters per second down here at the bottom. Now, how long did it take? Oh, we don't care, right? We don't care how long it took. Let's say it took 10 seconds. Why not? Okay. Now, when we do our calculation, we take our final speed, 5 meters per second, minus our initial speed, which is 0, thankfully. That will get rid of itself here pretty soon. And we divide that by our time, 10 seconds. So, you guys could do the math there. 5 minus 0 hopefully is still 5. And 5 over 10 is going to be 1/2. 1/2, okay? Or 0.5, whichever way you like to see it. And our unit turns to meters per second squared. Now, before we haven't really talked about the unit because it was pretty self-explanatory. Speed is measured in meters per second, just like miles per hour is measure of speed. However, this one is a little different, meters per second squared, okay? So let's look at this again. We're going to do it again over here real quick. Okay, so meters per second over seconds, okay? Meters per second over seconds, okay? Now, if we do that thing we did a little bit ago, we do a couple videos ago, times the reciprocal of seconds over 1, which is 1 over seconds, equals m over s squared, okay? So that shows us how we get to meters per second squared. But what does that mean? What does acceleration mean? Well, that means you are going to change your speed by this amount, whatever's on top, every second. So over here, what that means is that after the first second, after 1 second, at t equals 1 second, your velocity would be increased from 0 to this much, 1/2 meters per second. At a time of 2 seconds, you increase your speed by that amount again. Okay, so your velocity after 2 seconds would be 1 meter per second, right? 1/2 plus 1/2 is 1. After 3 seconds, we find that our velocity will be increased by this much again. So it's going to be 1 plus 1/2, so 1.5 or 3/2. At this point, I can write decimals because usually people start freaking out at fractions that are big. 1.5 meters per second. After a time of 4 seconds, we add another 1/2 on to our speed here, so our speed is increased now to 2 meters per second, and so on and so forth until after 10 seconds we find ourselves at 5 meters per second. So there is our acceleration. Now, Our acceleration in this particular case is going to be a constant acceleration. Now, the reason we know this because acceleration is the slope of a velocity time graph. Let's take a look at the slope here. Does this graph change over time? No, it does not. Okay, so this slope is a constant slope. And that will cause us to have a constant acceleration. Okay, constant slope there means constant acceleration. Okay? However, if we did have a velocity graph that was a little different, okay, let's say that we had a velocity graph that kind of curved, okay? We increase our speed like slowly or something. Okay, let's just stop it right there. It doesn't really matter. Our acceleration right here at the beginning would be 0, right? And then as we slowly increase, our acceleration would increase because it is the slope of this velocity time graph. And then eventually our acceleration would become larger right there. Okay, so acceleration can change over time. Most of the time in this class, we will be working with a constant acceleration, which leads us into our next section.